Welcome back. In this video lecture, we will see how to solve initial value problems with the Laplace transform and how powerful it is. But in order to do so, we need very important property related to differentiation. In fact, the property is the following one. Let's say we have a function that is admissible, so a function that we can compute its Laplace transform. So I have f of t that has a Laplace transform, capital F of s, and we want to compute the Laplace transform of f prime of t, the derivative of f. And it can be proven, and it's pretty easy to show, that what in time is computed derivative in the frequency domain is just multiplied by s. Wow! I will repeat that. You see here, the Laplace transform of f of t, the Laplace transform of f of t is capital F of s. When in time domain I compute a derivative, that sometimes is difficult, a little bit hard. Nobody likes to compute derivatives, okay? Not by hand, yeah? Okay, so what in time is computing a derivative in the frequency domain, this f of s, is just multiplied by s. Okay, I need to do some subtraction of a constant value, but wow, that's a very important property. What in time domain is derivative, taking the derivative in the frequency domain is just multiplying by s. That's going to be a very important property that will make differential equations very easy to be solved with this powerful tool that is the Laplace transform. You can check the proof, okay? It's pretty easy to follow, and I will just go straight to the property for higher derivatives, okay? It can be proved using induction that for any derivative of order n, okay, the Laplace transform looks like this. Maybe it's easier to start with the second derivative, okay? If I want to compute the second derivative of f, then I can use the previous. I know that the Laplace transform of f is capital F, and we already saw in the previous slide that the Laplace transform of f prime is just multiplied by s, capital F, and maybe subtract this constant. Now, here, we will use this, okay? Remember that f prime prime is nothing else but the derivative of f prime, yeah? So, I will apply here that the Laplace transform of f prime prime is s times the Laplace transform of f prime, the Laplace transform of f prime, minus f prime 0. Try to understand this, okay? I'm just applying this to a function that it is f prime prime, okay? I hope this is clear. So now I will apply this definition again, this property again, but here in this Laplace transform of f prime. So the Laplace transform of f prime now is pretty easy here. Is changed by this property here, and what we get is, doing the multiplication here, I get s squared times f of s minus s f of 0 and minus f prime 0. So at the end we get this formula here. So the Laplace transform of f prime prime, so what in time means computing the second derivative in the frequency domain is just multiplying by s squared. Maybe also subtracting some constant values here, minus s f0. Well, this depends on s, and minus f prime 0. So this is a very important property, and we can compute this in general, and that's what you have here, okay? When I compute the nth derivative in time, in the frequency domain translates to multiplying by s to the power n, and subtracting you see here decreasing exponents for s, so Sn, Sn minus 1, Sn minus 2, and it goes down to times S n minus n. N minus n is 0, and s to the power 0 is 1. So that's why it's not written, yeah? So these exponents just go and decrease 1 each time. And the function f0 appears here, the function, then the derivative of the function at 0, and now this increases, and it increases up to the derivative n minus 1, okay? So this is the definition, and we will see this is very, very handy. This property is very important to solve initial value problems. Now remember, what's an initial value problem? An initial value problem is a differential equation plus an initial condition. Here I'm trying to do it for a very simple problem. This is the ODE. It is a first order ODE. That's why we only have one initial condition. The ODE plus the initial condition is what we call an initial value problem. What we have seen in this course in order to solve differential equations is that to solve these, first we try to find the general solution, and then we impose the initial condition of the problem to find the specific values for the constant. Now, we will see that we will avoid this way. We will not solve the initial value problem in this way, remaining in the time domain. We are not going to do that. Instead, we are going to do a loop here. And this loop requires going from time domain to frequency domain. So here we are using the Laplace transform to go this way. So what we are doing here is we compute the Laplace transform of the whole ODE. So we compute the Laplace transform of y prime t minus yt. And as this is an equation, the Laplace transform of the left-hand side must be equal to the Laplace transform of the right-hand side. Now, what I have done in this step is go from time to frequency domain. Now, here is where the magic of the Laplace transform appears. Here, the Laplace transform is a linear, has the linearity property. So I can do this a little bit slower, and using linearity, this is the Laplace transform of y prime t minus the Laplace transform of y equals the Laplace transform of 0. Now, what is the Laplace transform of y prime? Remember, the Laplace transform, when we use the derivative here, if yt has a Laplace transform that is called capital Y of s, following our convention to use capitalized letters, then the property of the derivative is telling me that in the frequency domain, what in time domain is taking derivative, in the frequency domain is just multiplying by s and subtracting the value of the function at 0. So that's what we do here. The Laplace transform of y prime is s times capital Y of s minus y0, and then minus the Laplace transform of y by convention is capital Y of s, and this should be equal to the Laplace transform of 0, that is 0 by linearity, yeah? So what we have here then, this is very important. This is not anymore a differential equation. This is an algebraic equation. Wow. So we switch it from a differential equation, which is very hard to solve, to an algebraic equation that we know how to solve algebraic equation from a lot of years ago, yeah? Not at the university. So now we can solve the algebraic equation, and solve it is as easy as isolating ys here. I will do it. If I isolate ys here, remember that y0 is equal to 1, okay? This one will go in the right-hand side with a plus. And then here ys is multiplying s minus 1. So s minus 1 will be divided here. And that's what we have in the slides, okay? So this step that we have followed from here to here, which is just solving an algebraic equation, okay, is very simple. And we are avoiding this step that is solving a differential equation, which is pretty hard. This is very easy, okay? The only drawback is that we need to go back. People want the solution in the time domain. We are very comfortable living in time domain. We want our solution of our initial value problem in time domain. So we need to go backwards. So we need to compute the inverse Laplace transform of the solution we get here. For this particular example, it's pretty easy because this function appears in the table of Laplace transform, and we know this is just the exponential of t, okay? So this is very important. You really need to understand this slide and this procedure. We will use it to solve a lot of types of initial value problems. The only thing that will increase in difficulty is going backwards, okay? I think that the Laplace transform will be quite easy to be computed, almost always pretty easy. The algebraic equation will be almost always very easy to be solved, just isolating ys. And the only part that can be a little bit tricky is the inverse Laplace transform, so going back to the time domain. Let me show you another example. We want to solve this differential equation. Now it's a second order differential equation. So that's why we have 1 and 2 initial conditions. The first thing is to transform the ODE to the Laplace domain. So that's why we apply the Laplace transform to the left-hand side, and that should be equal to the Laplace transform of the right-hand side, okay? Now here we will use, to go from here to here, we use linearity. Oh, it's already written here, okay. So we use linearity, and to go from here to here, we are just using the property of differentiation, okay? You can check that the Laplace transform of y prime prime is equal to this term here, okay? It's very important that you understand this and that you do it properly. Then the Laplace transform of yts, by convention, I prefer to use this other notation, which is shorter. And the Laplace transform of t appears in the table of basic Laplace transform and is 1 over s squared. So basically now we can introduce here the initial conditions of the problem. We know that y0 is equal to 1, and we know that y prime 0 is equal to 1. So we substitute the initial conditions and we get this equation. Now from here we will isolate ys. We will solve the algebraic equation. Okay, this is very important. This is not anymore differential equations. They are no derivatives at all. This is just an algebraic equation. So we just isolate the unknown, which is ys, and we get this thing here. Now, as you can see, what we have obtained here does not appear in the table of basic Laplace transform. So we really need to work out a little bit in order to go back and find the solution of the initial value problem, yt, which is the inverse Laplace transform of this thing, ys, that we have here, okay? So that's the last step, which is to compute the inverse Laplace transform of this thing. In order to do so, remember that when we have rational polynomials, what we do is to use partial fraction decomposition. You need to review that in your notes from Calculus 1. Here we have, for example, root 2 and 2 simple roots. So that's why the first one, which is a second order root, has these 2 terms associated, and the simple roots have only 1 term associated to each one of them. And you solve this in order to find the values of A, B, C, and D. Then it's pretty straightforward to compute the inverse Laplace transform, because the inverse Laplace transform of 1 over s, 1 over s squared, 1 over s minus 1, and 1 over s plus 1, they all appear in the table. They are the inverse Laplace transform of t, the exponential of t. Oh, sorry, I want to explain this. The value of a is 0, so this term vanishes, okay? So t comes from 1 over s squared, the exponential of t comes from s minus 1, and the exponential of minus t comes from s plus 1. And then they are multiplied. They are multiplied by minus 1 here, 3 over 2, and 1 minus 1 over 2, minus 1 over 2, that were obtained from the partial fraction decomposition. So that's what I wanted to cover today. Thank you very much, and see you in the next lecture. Bye-bye.